19, 1 and 2. 1, we're in straight lines. 2 is diffraction, D-I-F-F, fraction. And then wave. 4 is Thomas Young, and we'll talk about that in just a second, what he set up. 5 is antinodal first, then nodal second. Spectrum is 7. Continuous spectrum is a better answer, but spectrum works for me. 8 is wavelengths. 9 is first order. 10 is second order. And then 11, we have the equation lambda is back. Lambda equals xd over L. We'll talk about that in a minute once you get your own papers back. Anybody have any question about how to score the paper you're looking at? 4 was Thomas Young. Young is enough. Last name is good enough. Anybody else a question about score? Back to owners they go. So we're back to an argument from history. So if you can think back a couple chapters, we had an argument where somebody said light is made of particles. Somebody else said light was made of waves. Who thought light was made of particles? Newton. Who thought light was made of waves? Huygens. And they had arguments back and forth. There were some arguments on both people's behalves. We don't need to relive that whole argument, but this is still continuing that same argument. So one of the things they were arguing about was diffraction. Newton was saying there wasn't really diffraction of light. Light didn't bend. But then along came Thomas Young in number 4 and said, actually, it does a little bit. So one, it feels like light travels in straight lines. It does seem to be so. If you go through a large opening, you do appear to get pretty sharp shadows. But if you go through some small openings, sometimes the edges get a little bit blurry. So diffraction of light is a thing. Diffraction, you might remember, key word is bending. So for number 2, you might want to underline the word bending, and we'll talk about the next quiz in a minute. But diffraction definitely has to do with light bending. So here's a Thomas Young situation. You'll have to draw this drawing next quiz. So you'd want to jot this down. So here's his scheme. He had some sort of a light source. He set up some sort of a barrier, like a piece of paper or a screen of some sort, and he cut a small slit in it so that some of the light could get through. Then he set up another screen where he made a couple clips in it. The next screen had 2 slits in it, but they don't line up with the first slit. They're kind of off staggered, one on each side. He sent some light through this first thing. You would think the light, if it went through this first slit, would just bounce into this barrier and go nowhere, and you wouldn't get any light on anything. And then he set up another screen a little farther down the line, but lo and behold, he not only got light, but he got a bunch of crazy stuff going on with this light. So I should have maybe lined this up a little better. There's a thing, I wrote CBL to abbreviate. Anybody pick up from the reading what that CBL, what's that an abbreviation for? Central bright line. So the central bright line should line right up with that first slit, as if the light went through that first slit and went through another gap there when there wasn't even a gap there. But you'd expect light going through that first slit to create a bright spot of light somewhere on a shadowy screen. But then there's also this alternating bright dark thing. So if your book is handy, 320 is a decent picture. Instead of holding your book this way on 320, go like this. And that's a fair representation of what's going on with this. That on the screen down yonder at the end of the line, there's this bright spot. The central bright line creates a bright spot where it's white light. What was white light when we studied white light back a couple sections ago? How did you get white light? How'd you get black? Or why does my shirt look blue? Let's start with that. Okay, it looks blue because blue is bouncing back at you. So I don't have anything up here that's black, but we've got some people out in the audience wearing black. Why does black look black? It's absorbing everything. Nothing is bouncing back. So what's white about it? Everything is bouncing back at you. If you combine all the other colors, you get white light. So what's going along this straight central path is all the colors are merging back together here, and you're getting white light. So in the center of this picture on 320, you're seeing a big white spot right in the middle where the light is all meeting for that central bright spot. If you go up a little bit above there, you see a dark band where there's not any light hitting it. You see another dark band below where light's not hitting it. If you go up, you'll see a bright patch again and a bright patch again. But that bright patch isn't just white light, it's like a little rainbow going on there. Okay, because every color is going to bend a little bit of a different amount than every other color of light. Each wavelength is a little bit different in frequency and speed and all those things. We've done that before, longest, shortest, fastest, slowest, that stuff. So each color kind of does its own thing. And right here we're getting a bright spot, but it's a rainbow. And then the picture then the picture does another dark band, and then it ends. If we had a little wider picture, you might get another rainbow up here. But what I'm doing here is I'm going like things kind of with a little bit of a bend to them. The central bright spot is bright, and then it's going to go dark, bright, dark, bright. When we go down, it's going to go dark, bright, dark, bright. On the screen, you get an image like this 320 if you're Thomas Young and you have this all set up. Question about the scheme? So if you understand that scheme, now the words maybe make more sense. Okay, so for 5, the antinodal lines are where you get constructive interference. That's the bright stuff. Okay, so the antinodal lines, that's constructive interference, meaning bright things. The nodal lines are where you're going to get destructive interference, so that's going to be the dark spots. So right next to the central bright line, you got a dark spot. That's what kind of line? Nodal. Then this bright would be antinodal, and so on and so forth. We had the word node, if you remember that. Like if I had waves going like this, what kind of interference was that? Constructive or destructive? Constructive, because when they meet, the thing's going to get bigger. If I sent you 2 valleys, that's constructive, because that valley's getting bigger. If I go like this, that's destructive. And if they completely canceled each other out, that was called a node. So nodal has to do with destructive interference if you want to try to link the things you already knew. 7, we talked about the spectrum. We saw the rainbow on 320. Each color being different is something that I mentioned, so you can figure out the different wavelengths of light depending on where you're going. First order and second order lines, these two right here would both be first order lines because they're right next to the central bright line. These are first order dark lines. These are first order bright lines. Then these would be second order darks. Those would be second order brights. So that's what that first order, second order thing is about. And then there's an equation. For the equation, I redrew the picture to just show you what the letters mean. So the distance between the slits at this middle screen or this middle barrier or whatever it's made out of, there's a distance between the slits here in the middle. That's what the D is. The D is going to be the distance between the slits. The L is the length of the first order bright line. So understandably, okay, the bright line, there's a little bit of a bend to it. It isn't exactly a straight line, but for the math, we're going to ignore that. And we're just going to measure the length from here to there for brightness. If we measure the length of that bright line, that first order bright line, that's the L. And then the X is on the screen itself. If you measure from the central bright white spot from the dead center of that white spot to your bright spot, you measure that, that's going to be your x. So if we go back to this picture, and you're never going to have to look at a picture, but if we look at this picture, the D would be the same for every color. The L is going to be a little different for each color if we're tracking to the rainbow, because you can see that the red is like higher up and the blue is lower down. So if you were doing measurements, the X for blue would be different than the X for red, because they're different heights away from the center of the white. Each color has a little different bend to it, so there'd be a little different D. That would cause a little different wavelength, or excuse me, same D all the way around, because the slits aren't moving. But since the X is changing for every color on the screen, the wavelength's a little different for everybody on the screen. So the homework's going to be having you find like certain wavelengths of certain colors, but not looking at pictures. They'll just give you your numbers. As always, just be careful that everything's the same units. If one of these is centimeters, just make sure they're all centimeters. If one of them's meters, make sure they're all meters. They need to be a consistent unit on this. Question about what any of this stuff means or what people are doing. This is more a history lesson than modern day. I mean, there are people in the modern day trying to like still decide if there is diffraction or not. But Thomas Young, this is a history thing where he's weighing in and giving some strength to the Huygens side of the argument. Nothing there? Okay, so homework, there's a 1 to 5. So homework 1 to 5 is primarily this equation, but I have a note on my paper that sometimes in this chapter we're going to need to get F figured out. Okay, so first of all, what does this lambda stand for? What is that? It's the wavelength. What did F stand for? Frequency. What old equation did we have that had like F's and lambdas in it? That had F in it, but yeah, not the lambda. There's one that has F in it and lambda in it. Memories of F's and lambdas in the same equation? Yes, C equals F lambda, where the C is a certain velocity. What is the C number? 3 times 10 to the 8th. It's the speed of light. So 3 times 10 to the 8th fits here. Frequency and wavelength, if you know one, you can know the other one. And apparently that's going to happen in some homework, because I threw a note on my bottom of my paper here that said, if F gets involved, UC equals F lambda from your old days. Question about understand. So 1 to 5 is coming. The read for next time, the quiz for next time is reading 19, 3 through 5. There's only 4 new points, but the quiz pops a good bit because there's just drawings and things going on here. So let me try to describe this for you. Again, 4 new points from 19, 3 to 5. 1, I'm keeping the same. 2, I'm going in reverse. What is diffraction? So bending and barrier would probably be the main words. We used to, I think, say bending of light around an object in its path. That's fine. That's what a barrier is. A barrier is an object in your path. That's different than a boundary. Refraction, we were always talking about boundaries, where you're going from one thing into another, like we send light in from air into glass. That's refraction. If we're sending light and it bends around something in the way, but it doesn't really change what it's in, that's diffraction. So diffraction, bending of light at a barrier, or bending of light around an object in its path, that's all fine. 3 isn't there anymore. 4 is still there, Thomas Young. Picture, I do 5 points for replicating this picture. So we want to go light source, single slit, double slit, central bright line, onto a screen, label that this is a screen, and then we're going to go dark, bright in both directions. 5, 6 is going to become a 6-point question. So it'll say name 2 kinds of lines. You'd say who versus who. Antinodal versus nodal. Tell what kind of, or it'll say define them. So nodal, I'd say the interference is constructive, and and nodal the destructive, and then tell whether it's bright or dark. The constructive one is going to be bright, and the destructive one will be dark. 7 stays the same. I'll follow up with why you get a spectrum, and the answer is each color diffracts differently. So spectrum is there for 7, follow up why each color diffracts a different amount. Each color diffracts differently, something like that. Instead of 9 and 10, I'll just say name and define 2 other kinds of lines. So you'd say first order versus second order. First order, you would just say directly next to central bright line. And you don't have to write out central bright line, you could write CBL. So the first order lines are directly next to the central bright line. Second order, you can just say farther away. So first order lines directly next to central bright line. Second order lines farther away. 11, equation stays the same. Then a 3-point follow-up, I'll ask what the letters are for. So for what the letters are for, I'd rather you not do this with picture, but do it with words. If the picture helps you come up with words, so be it. But the D, you could explain how. How could you explain the D? Distance between the slits is perfect for that. So D equals distance between the slits. How about the L? How could you explain the L? Yeah, what could we call this line? What kind of a line? Length of the blah blah line.
Yeah, hypotenuse.
Now let's think about this drawing. We're measuring this line essentially. How could you know I was talking about this line and not any of the other lines? How would we know it's this line I'm following?
Yeah.
That's true, but there's 2 of those.
First order.
First order. Yeah, it's the length of the first order, which one? Bright line. So L, length of first order bright line. Then the X, let's do the preview on the screen, because the X is found on the screen. It's on the screen the distance from central bright line to first order bright line. So X is distance on the screen from first order bright line to central bright line. And having this picture already drawn may help you do that, the words for those, and not have to like, personally, I would not be memorizing those phrases. I'd be like looking at the picture and talking my way through it. But the D is the distance between the slits, the L is the length of that first order bright line, the X is the distance on the screen from first order bright line to central bright line. And then a final 2-point question that has to do with this, I'll say once you have the wavelength, what else could you get? And you'd say the frequency. And I'll ask you for what equation? And that's the equation for figuring out frequency. So again, once you have the wavelength, what else can you get? Frequency. How? There we go. After you read 3 to 5, guess what? Chapter's over. It's out as quick as it's in. Yeah, there is a test for this. So next week we'd be looking at some 3 to 5, a little bit different drawing, a little bit different equation in the next read. And then we just sort of put it together, a little chapter review, a little practice test for me, a little bit of test toward the end of the week. But chapter 19, it's a quickie. Anything I can do to clarify either what in the world this stuff means or details of what I'm asking you to do for quiz or homework. All right, shut that down.